Hello and welcome to this film, which is all about using cycles or Hess's Law cycles to calculate enthalpy changes. This is the 8th in a series of films about the standard level energetics topic, and hopefully you've seen the 7th film where we go through these kind of cycles in principle. If you haven't, I suggest you watch that before you watch this one, because I'm going to be assuming some knowledge from that film. So hopefully in this film you'll understand not only how to use the cycles, but also how to construct them from equations that you might be given. Okay, now let's just have a very quick reminder before we start of what Hess's law is. Hess's law says that if I'm going from A to B, the energy change will be the same regardless of whether I go via C. Okay, so we can construct these cycles and know that the enthalpy change for a process is the same regardless of the route taken. Now, here are some equations that I'm going to turn into a cycle. Okay, we're given the first one and we're told that we don't know the enthalpy change for that process. So we'd like to find it. Okay, so I'm going to put that enthalpy change here and I'm going to use this as the first side of my triangle. I could use any side I wanted, right? But it's important that if I put the reactants and products a particular way round, that the arrow in my cycle points the same way as it does in this equation, because otherwise I'm going to be finding the reverse process. Okay, so I'm going to put that arrowhead pointing that way. Okay, now, why bother doing this kind of thing? Well, because if you want to find out what the enthalpy change is for turning carbon and oxygen into carbon monoxide, that's a virtually impossible reaction to do, because inevitably some of your carbon will turn into carbon dioxide. Okay, and in actual fact, to get carbon and oxygen to turn into carbon dioxide, you need not just a half O2 but a whole O2. So I'm just going to put another half O2 here, so that on this side of my triangle I've got this reaction equation. Okay, so carbon plus 1 O2 turns into CO2. The arrow is going that way. Okay, it's going from the carbon and oxygen to the CO2, and I know if it's going that way that this process is minus 393 kilojoules per mole, or the enthalpy change for that process is minus 393 kilojoules per mole. Now you might think, well, I've upset the balance of this equation. Well, yes, you have temporarily, but notice there's another equation here, and that says that carbon monoxide will turn into carbon dioxide if you add a half O2. And now by doing that, I've actually redressed the balance of this first equation. You might think, well, hang on a second, won't that change this energy change? Well, no, because if I just add a half O2 on both sides of this equation here, it shouldn't affect the energy change because nothing's changed with that a half O2. Okay, but getting back to this process here on this side, so here is my reaction equation for CO plus a half O2 turns into CO2. That's just that equation written there, okay, right? And I know that going in that direction, it's minus 283 kilojoules per mole. So now I'm going, in my unknown reaction, I'm going delta H question mark is equal to, I'm going from there to there. So if I go via here, I'm going with this arrow. In other words, I'm doing this reaction in the way that this energy change says. So that's going to be adding minus 393 and then subtracting, because I'm going against this arrow, I'm doing this reaction in reverse. So I'm going to be changing the sign of that number, right? So I'm going to be subtracting minus 283. That's like adding 283, and that is equal to minus 110 kilojoules per mole. So hey presto, I found the enthalpy change for a reaction that I can't really carry out by using the enthalpy changes for two reactions that I can easily carry out. Okay? And not only have I used the cycle in the way that we were shown in the last film, I've also constructed it from the equations that I was given. Now here's a slightly more complicated example, and again we're given an equation that we're trying to find an enthalpy change for. Just to show you that I could put this on any side of the triangle that I choose, I'm just going to put it over here this time, okay, and I'm going to write PCl5 here. Okay, makes PCl3 and Cl2. Okay, and this is the enthalpy change that I'm trying to find out. We're going in the PCl5 to PCl3 direction, so this arrow has to be pointing that way. Okay, now let's write this equation here along the top because I've got PCl5 in it, so let's have PCl5. I actually need 4 PCl5s, so I'm going to put in a 4 here, and it's going to turn into P4 and 10 Cl2s. And I know that if that happens in that direction, so here's my reaction equation for this process, that the energy change here is 3438 kilojoules per mole. Okay? What about P4 and Cl2 reacting? Oh good, they turn into PCl3. And notice that if I only had 6 Cl2s here, I'd have 4 left over. So P4 and 6 Cl2 will turn into 4 PCl3 and 4 Cl2s, right? Because I've got these 4 Cl2s left over. And if I do that process in which direction? Well, from the P4s to the PCl3, so arrowhead pointing that way, then the energy change, or the enthalpy change, is minus 2439 kilojoules per mole. And now I can say to myself, right, this enthalpy change here, going from this corner to this corner, is the same as going there first and then there. But notice what's happened. By writing these other equations in, I've ended up with 4 PCl5s and 4 PCl3s and 4 Cl2s. And that's 4 times this reaction. So the enthalpy change will be 4 times as great. So in other words, when I'm finding this unknown enthalpy change, I want to do 3438. I'm adding that because I'm going with that arrow. I'm adding this because I'm going with this arrow. So plus minus 2439 is minus 2439. But then I'm dividing the whole lot by 4 because the enthalpy change I'm trying to find is for only a quarter of this equation. And if I go ahead and do that, I get 999 divided by 4, and that's 249.8 kilojoules per mole to 4 significant figures because I've got 4 significant figures in my data. Okay, so that's, I suppose that last one is quite complex, but remember, there is a mathematical kind of shortcut to doing these cycles, and we'll be showing you a few examples of that in the next film. But for now, hopefully you've seen how we can construct these cycles from reaction equations. If you can do this, you'll get a much better understanding of what Hess's law means, even though you can often use the mathematical shortcut. And then, like in the last film, we've used these cycles to actually calculate some enthalpy changes. If there's anything you want to ask about or anything you want to comment on, please feel free to come and see me or to post a comment on YouTube.